Hello everyone, welcome to another lesson in physics. And today, like the previous lesson, we are focusing on momentum and impasse. Now if you remember, in the previous lesson we stopped at impasse momentum theorem, which basically says the product of net force and contact time is equal to change in momentum. And what is change in momentum? The product of mass of an object and change in velocity. This is where we stopped, and we looked at applications of impasse momentum theorem, which basically is what I'm talking about here. Impasse momentum theorem. Now I want to look at two more examples. In the previous lesson we looked at one example. Today I want to look at two more examples. So example one, we are looking at a ball which is bounced off the wall perpendicularly. So if you remember, in the previous lesson I used a 0.4 kg ball bouncing off the wall perpendicularly. This time I want to hide that velocity there, which is our initial velocity, and I want to give this one here, which is 6 meters per second. The mass remains 0.4 of a kilogram, and I want to say that this time the force that the wall exerts on the ball should be given. So the wall exerts a force of 320 newtons to the left. That's information number one. Information number two, the ball stays in contact with the wall for 0.02 of a second. Now the question number one, let's call it A, is determine impasse on the ball. But B, we are going to say calculate the velocity with which the ball hits the wall. So this is number one of our two examples for today on impasse momentum theorem. Now let's look at the answers. We choose direction as our positive direction, so either direction of final velocity or direction of initial velocity. In this case, like the previous one, I'm going to choose direction of final velocity as my positive direction. So it's number one. A, determine impasse on the ball. Now we know that impasse is the product of net force and contact time, because that's what we know. And we're using this formula because we've been given net force, the force that the wall exerts on the ball, and we've been given contact time. So we can simply say the force that the wall exerts on the ball is positive 320 newtons multiplied by contact time, which is 0.02. And if you do your maths here, this is going to be positive 6.4. And we said last time that impasse is measured in newtons seconds, and we're going to say to the left. Why to the left? Because the answer that we have here is positive, and we chose to the left as positive. So that should be our impasse on the ball. Next, the question is demanding us or requiring us to calculate the speed or velocity with which the ball strikes the wall. Now that requires us to use impulse momentum theorem directly. So let's go to page 2 for today. This is page 1. Now moving to page 2. And page 2. Now, right. So we're now going to say number B. What we know is impulse, which is change in momentum, is equal to the product of mass and change in velocity. Do we know mass of the ball? Yes. Do we know change in momentum? Yes. Change in momentum is equal to impulse from the impulse momentum theorem. So we're going to use 6.4 Newton seconds to the left as our change in momentum. So positive 6,4, we're still taking to the left as positive, is equal to mass of the ball is 0,4 of a kilogram. And I'm using square brackets here because velocities are actually vector quantities. The signs don't have to be the same. They actually, in most cases, are different. Like in this case, the signs should be different. Final velocity is, if you check here, 6 meters to the left, and we chose to the left as positive, so the 6 must carry a positive sign. Positive 6, that's the final velocity. Now, initial velocity, they just said v. So we don't know what the value of initial velocity is, and that's what they require us to find. We're not going to put any sign in front of it. We're just going to put v there. Please take note of that, because it is v itself that should be minus. So we don't put another minus in front. Right, let's solve for v now. How do we do it? Well, 6,4, we're supposed to divide by 0,4 on both sides. 0,4 multiplied by, now we can open the smaller brackets, the round brackets. It will be 6 minus v, like so, and we're dividing this by 0,4. These cancel on the left hand side. It's supposed to be I think 16. Let me just be sure my calculator. Right, I'm gonna use 16 here. So this over that 6,4 divided by 0,4 should be 16. 64 over 4 is 16. Yes, so 16 is equal to, and what do we have here? We have 6 minus v, and making v subject of formula, it will be v equals 6 minus 16. And so our v is going to be minus 10 meters per second. In which direction? Well, we chose to the left as positive. We chose left as our initial direction of motion. Please take note of this. We chose left as our positive direction, left. So our final answer that we get, without processing it, is going to take the same direction. So we're going to say here to the left. Now, the minus sign is basically saying that this is not to the left. So we change the sign from minus here to the opposite of minus, which is positive, and we have to change that to the opposite of left, which is right. So therefore, v is going to be positive 10 meters per second to the right. So what am I saying? I'm saying that when you're dealing with vectors, your raw answer that you obtain must always have the sign, the direction you chose as your positive direction. Why? Because when you're substituting velocities in this formula here, you are using that direction as your positive direction. So your answer must respect that. However, if the answer is negative, it is suggesting that the direction you've chosen as the positive direction is actually not the direction in which the ball is going. As you can see in the diagram, the ball is actually going to the right. So the minus sign changes to the opposite, and the direction we chose here changes to the opposite. In most cases, they ignore this part. They just find minus 10 and then they come straight here. But please take note of that direction there in our raw answer. This is a processed answer, that's a raw answer. Right, so this is the end of example number 1. We were required to work out impulse. We just applied the formula for impulse, which is the product of net force acting on an object and contact time, and we got our answer there. the second part required us to work out the velocity with which the ball strikes the wall. And what is critical in this one is to remember that when you're substituting the unknown v there, you do not put the sign in front of it. You work with this unknown, and then the answer, the sign will come out on its own. Right, example number 1 ends there. Let's look at example number 2. Now, example number 2, I want to talk about still application of impulse momentum theorem. Example number 2, a car of mass 1,200 kgs is moving east at 15 meters per second. Full stop. The driver of the car applies brakes, and the car comes to a stop in 8 seconds. The question says, determine the car's braking force. So this example here, we're actually supposed to use impulse momentum theorem, but you can also use equations of motion. The assumption is the car is moving on a straight line. Otherwise, you'd not be able to use equations of motion, because equations of motion apply only for linear motion, or apply only to linear motion. Now, in this case, we're going to use impulse momentum theorem. So we're going to say that here is a simple diagram of our car. So our solution or answer, a simple diagram of our car moving east, and of course the understanding is there is your compass, east at 15 meters per second. The mass of the car is 1,200 kgs. This car comes to a stop. It comes to a stop somewhere this side, and therefore we can say that V initial is equal, if we choose to the right as positive, will be positive 15 meters per second. V final is actually going to be 0, because the question says the car comes to a stop, and we know the mass of the car, and we are told contact time delta t 8 seconds. In other words, the tires of the car are in contact with the ground or the floor, the tarmac, for 0.8 of a second as the car comes to a halt. So we're going to say now, after putting down the information provided, we're going to say F net times delta t equals delta p. That's impulse momentum theorem. Do we know F net? No, that's our braking force. Times, do we know contact time? Yes, they have told us that it's 8 seconds. And this is mass times V final minus V initial. Do we know mass? Yes, 1,200. Do we know V final? Yes, it comes to a stop. It must be 0. Do we know V initial? Yes, initial positive 15, because we took the right or east as positive. So it has to be positive 15 here. So F net times 8 seconds equals this. So 8 F net is equal to, expanding this, it should give us, okay, let me not simplify it for now. I'm going to say minus, because this is minus 15, times that, it will be minus 15 times 1,200. and we have to divide both sides by 8. And these cancel here. When you divide there on the right hand side, you're going to get minus 2250 newtons. Direction, remember what I said in the previous example, east. The minus sign tells you it's actually not east, so we must change that to 2250 newtons west. That makes a lot of sense because this car is coming to a stop. It's going east and comes to a stop, and therefore the net force must be opposing motion. The braking force must be opposing motion. So this marks the end of example number 1. This was number 2 actually. End of example number 2. Now we're moving on to Newton's second law in terms of momentum again. If I take you back to this formula here, F net is equal to delta P over delta T. I told you this formula is very critical. Let's look at applications of this formula in our everyday lives. So we have 1, landing area. For long jump is filled with sand. Why? The reason is to increase contact time while change in momentum stays constant and net force is decreased. The reason why we're aiming to decrease net force is because it's net force that causes damage. It's the net force that causes injury. So scientists have devised mechanisms and techniques to make sure that they minimize the impact of net force on human beings in different circumstances, like long jump and high jump. So for long jump, the landing area is filled with sand in order to increase contact time while change in momentum stays constant, and therefore net force decreases because net force is inversely proportional to contact time. And I must say that these 3 points remain the same for all the examples I'm going to give here. What are the 3 points? 1, delta P remains constant. Change in momentum stays constant. What are we saying? Delta T increases. Point number 3, F net decreases because F net is inversely proportional to contact time. These 3 points, if a question comes on any of the things I'm going to list down here, these are the 3 points they are looking for, and it will be 3 marks and sometimes 4 marks if the examiner is kind enough, but otherwise it will be 3 marks. A typical question would be, using principles of physics, explain why the landing area for long jump is filled with sand. And you're going to say, in order that contact time is increased while change in momentum stays constant, and therefore net force decreases because net force is inversely proportional to contact time. You have to mention that statement there. Net force is inversely proportional to contact time. You can list these things, these points in any order that you want. In most cases, I encourage learners to list them in this order. Change in momentum stays constant, sand increases contact time, and therefore net force decreases because net force is inversely proportional to contact time. So landing area for long jump, and we also have filled with sand there. We also have landing area for high jump. They put what we call a crash mat there. Is covered with a crash mat. So the crash mat increases contact time while change in momentum stays constant and net force decreases. We also have boxing athletes, boxers. What do they wear? They wear gloves. Why? In order to increase contact time when the blow is landing, contact time is increased, changing momentum stays the same, net force decreases. And so the risk of injury is actually minimized. We also have crumple zones. Modern cars are manufactured with crumple zones in front. The crumple zone squashes in when the car is involved in a collision. By so doing, contact time is increased while changing momentum stays constant, and therefore net force decreases because net force is inversely proportional to contact time. We also have arrestor beds. Modern freeways are constructed with arrestor beds. If the brakes fail of a truck, the brakes become dysfunctional as you're moving down highway. The arrestor beds, they are where you actually take an off ramp into the arrestor bed filled with material that will bring your truck to a stop. So arrestor beds, and how do they do that? By increasing contact time so that net force decreases. And when net force decreases, the car or the truck will eventually come to a stop. I can give you many more examples, cases where this formula here is applied. I'm going to leave it to you to try and find many more cases where you can apply this. I've just given you landing area for long jump, landing area for high jump, boxers, crumple zones, and we have what we call arrestor beds. You can also talk about arrestor belts. You can also talk about many more examples that one would give where that formula is applied. Let me think of one more. It would be, for example, a goalkeeper will bend backwards when he's making a save in order to increase contact time between the ball and his body, the chest. By so doing, net force decreases because contact time is increased. Ballet dancers, another example, they bend their knees when they're landing in order to increase contact time so that net force decreases while changing momentum stays constant. So you can find many more examples on that one. Right, after this, I want to talk about what we call a system in physics. So a system. Now, we define a system in physics as a collection of objects. It is a collection of objects. That's how we define a system, a collection of objects. So, for example, if you have a car moving on a road, and probably there are people inside there. In this case, when we talk about a system, we are looking at the road on which the car is moving, the car itself, people inside, and air around it constitute what we call a system. And there are two types of systems. We have what we call an isolated system, and we have what we call a non-isolated system. So what is an isolated system? We define an isolated system as a system in which net external force is zero. So it is a system in which net external force is zero. A typical example of an isolated system is where there is no frictional force. That is a typical example of an isolated system. No frictional force, no tension. In other words, if you have a towing system, that cannot be an isolated system because there's tension there, and tension, just like frictional force, applied force, those are examples of what we call non-conservative forces. We will define non-conservative forces and conservative forces when we start looking at work energy and power. But in this case, when these forces are not in the system is isolated. So, but otherwise, if you have frictional force, applied force, tension, then the system becomes non-isolated. And therefore, the net external force in that case is not zero. But in this case, where there are no non-conservative forces, for example, if you don't have frictional force, you don't have applied force, you don't have tension, then we can say the system is isolated and therefore net external force is zero. Now, so I've just given an example of I've just given examples of non-isolated system, and therefore let me go straight to, because this is the most important of the two systems. This is the more important of the two systems, because in this one, that's where total linear momentum is conserved. In the other one, non-isolated system, total linear momentum is not conserved. But in this one, it is conserved. So let me state the law of conservation of linear momentum. So we say the law of conservation of linear momentum. It states that in an isolated system, total linear momentum, total linear momentum remains constant. It states that in an isolated system, total linear momentum remains constant. Now, let's prove this one. So we're going to look at a case where we have a collision. So before a collision, let's say we have two cars approaching each other. Let me call this car A, moving at initial velocity of V initial, and it has a mass of ma. And there's another car coming from this side. Let's call this car B, traveling at initial velocity. So this is V initial of A, and this will be V initial of B. This is before the collision. So before collision, this is head on. During collision, we have this kind of scenario here. Cars collide over here, and what we know is that this car, which is B, exerts a force on car A in that direction. So this is force on A, and this car A exerts a force on car B in that direction. During the collision, let's call this F on B due to A. And let us say that after the collision, the cars are separated. This is our car B, and let us assume there is no change in mass. This remains car A with mass ma, and this is car B with mass mb. And let's say this has a velocity of v final of A, and this one has a velocity of v final of B. So we are saying the system is isolated. It means net external force is 0. So we can say, therefore, F net is equal to 0. Why? System is isolated. In other words, there's no frictional force. Net external force is 0. What does it mean? We have two forces here. It means that Fa plus Fb must be equal to 0, because net force is 0. And what is net force? We define net force as the sum of all forces acting on a system. And therefore, from here we can say Fa is equal to minus Fb. And let us say that the collision lasts for delta t of a second. And these two cars, the only forces acting on them are these two forces. So we can comfortably call them their net forces. So Fa, we can say it's the net force on A. So this can change to F net on A is equal to minus F net on B. Now, if I multiply both sides by delta t, you say, why do you multiply both sides by delta t? Because I want to move to momentum. Remember, we're talking about the law of conservation of linear momentum here. So this is F net on A times delta T. What you do on one side of the equation, you do the same on the other side, minus F net on B times delta T. Now, notice that this basically is change in momentum. It's impulse, and that one is also impulse. So this move on. I'm not gonna number the page there. We're just gonna correct the pages at the end. So, and at the moment we're moving on. So I can say, therefore, this means this part here is actually change in momentum of car A is equal to this. I can call it minus change in momentum of car B. Remember, impulse equals change in momentum, impulse momentum theorem. And what is delta P of A, change in momentum of A? It's final momentum of A minus initial momentum of A, minus, what is this? Final momentum of B minus initial momentum of B. Let's expand the right hand side. So we have P final of A minus P initial of A is equal to minus P final of B plus P initial of B. Now transpose, take this one to the other side and this to the other side, or add this and that on both sides. What you're going to get is P final of A plus P final of B is equal to, if you take this one to the other side, it's going to be P initial of A plus P initial of B. What does this mean? It means that when we sum up momenta of these two cars before they collide, the answer will be the same as when we sum up momenta of these two cars after they have collided. Why? Because the system is isolated, net external force is 0. So we can continue here and say this is the same as total, sigma notation there, Greek capital S for sum. So sum of momenta final. So total final momentum is equal to total final momentum, or momenta. In this case, we're summing up, so it forms one momentum. Total final momentum is equal to total initial momentum. This is the law of conservation of linear momentum. This is the law of conservation of linear momentum. Formula. Let's state the law of conservation of linear momentum again. It states that in an isolated system, total linear momentum remains constant. Here it is. It states that in an isolated system, total linear momentum remains constant. And we have seen it here. Momentum, total linear momentum before collision equals total linear momentum after collision. There it is. That's the law of conservation of linear momentum. At this stage, I'm going to look at, before I move on to examples on the law of conservation of linear momentum, since we have spoken about collisions here, let's speak about types of collisions first before we go to examples on the application of the law of conservation of linear momentum. So types of collisions. We have basically two types. Number one, elastic collision, elastic collision. Elastic collision. How do we define an elastic collision? It's a type of collision in which both total linear momentum and total kinetic energy is conserved. So the defining condition is that total kinetic energy is conserved. So let me define it. It is a type of collision in which both total linear momentum and total kinetic energy are conserved. In other words, they remain constant. Elastic collision. Total linear momentum is conserved. Total kinetic energy is also conserved. So let's look at the mathematical conditions for these two. So here we go. So what am I saying? I'm saying for elastic collisions, number one, total final momentum equals total initial momentum. Number one. Number two, condition number two, total kinetic energy, EK initial, total EK final. Now this is the one we use to differentiate the two types of collisions, because this one is conserved in both elastic and inelastic. Total linear momentum is conserved in both elastic and inelastic, but total kinetic energy is conserved only in elastic. I'm going to repeat that. I'm saying total linear momentum is conserved in both elastic and inelastic collision, but total kinetic energy is only conserved in elastic collisions. In elastic collisions, EK total kinetic energy initial is not equal to total kinetic energy final. So we're going to use this. Whenever they say the collision is elastic, this is the information they're giving you. It means this is the one that you must use to determine whatever they want you to determine. Let's look at type of collision number two. Inelastic collision. Do not confuse the type of collisions in chemistry. In chemistry, we say effective and ineffective collisions, but here we say elastic and inelastic collisions in physics. So in physics, elastic and inelastic collisions. In chemistry, effective and ineffective collisions. So in elastic collision, we say it's a type of collision. It is a type of collision in which total linear momentum is conserved, but total kinetic energy is not conserved. So what are we saying mathematically? We are saying total final momentum equals total initial momentum. Condition number one. Condition number two, we are saying total kinetic energy initial is not equal to total kinetic energy final. This is the defining, the one that we use to define inelastic collisions. The defining statement or equation. Now let's look at examples on applications of conservation of linear momentum. Let's look at examples on this. So I'm going to give example number one, and I'm going to say that we have Andrew here on a skateboard moving to the right with a speed or velocity of 4 meters per second. The mass of the skateboard and Andrew together 60 kgs. Now there's Ben standing somewhere here, a little boy Ben, whose mass is 40 kgs. and Andrew picks up Ben and they move to the right together. Let's draw that scenario here. So here is Andrew and here is Ben. They're moving together going that way with a velocity v. Notice that now their combined mass is going to be 100 kgs. The examiner will not tell you that, you will have to know. The question is, determine the speed. Determine v. So we're saying Andrew is moving east. If I put the compass there, north, east, Andrew is moving east on a skateboard at 4 meters per second. The mass of Andrew and the skateboard is combined mass is 60 kgs. And Andrew picks up Ben. This is Andrew. Picks up Ben along the way, whose mass is 40 kgs. The two move to the right together. Determine the speed or velocity at which the two move to the right together. So this gives us an idea of what we mean when we talk about collisions. So collisions is not just two objects bumping into each other. If someone grabs, like this one is moving east and then picks this one up, that's a collision in physics. Or a bag of cement thrown into a moving car, that's a collision in physics. A bullet fired from a gun, that's a collision in physics. So you would have to look at many scenarios, many cases where the law of conservation of linear momentum is applied. It's not just two objects bumping into each other. Please take note of that. Now, how do we answer this question here? They don't tell us that the system is isolated. We're going to assume that the system is isolated. If they told us that the system is not isolated, they would have given us some energy. We would have worked with kinetic energy. But in this case, we have to use the law of conservation of linear momentum. So we choose direction. Our answer, choosing to the east as our positive direction, we can say always start from here. Always start from there. And what are we saying now? We're saying mass of Andrew times final velocity of Andrew plus mass of Ben times final velocity of Ben is equal to mass of Andrew times initial velocity of Andrew plus mass of Ben times initial velocity of Ben. Let's substitute what we know. Take note, mass of Andrew is 60. This is what I'm going to do. Mass of Ben is 40. Mass of Andrew is 60. Mass of Ben is 40. Let's put in what we know. And again, the assumption is Ben is initially here, stationary, standing. Ben is stationary there. So, at this stage, notice now, they form a system. They move together as a unit to the right. So, V final of Andrew and V final of Ben is the same. Is our V up there, given in the question. Here it is, there. So, we're going to say that here is the same velocity. When it comes to the other side here now, we have to say, what is the initial velocity of Andrew? Well, the question has given us 4 meters, and it's the right, which we've chosen as positive, so the 4 must carry a positive sign. What is the initial velocity of Ben? Well, Ben is initially stationary, so the velocity initial velocity of Ben is 0. If you work on this one, you're going to get 100 V is equal to 240. If you divide by 100 both sides, you're going to get V equals positive 2,4 meters per second, and of course east. So the two move together to the east at 2,4 meters per second. This makes sense because initially Ben alone was moving at 4. Andrew alone was moving at 4 meters per second. After picking up Ben, naturally you would expect the speed or velocity to decrease, and physics confirms it. And here it is, 2,4 meters per second east. Please take note, I'm putting the positive sign and the direction every time you're dealing with vectors. The question does not say determine the magnitude. In this case, it simply says determine v, which is a vector quantity, so it has to have both magnitude and direction. Unless they said determine the magnitude, I would not have indicated the east there, I would not have indicated the plus sign in that case. Right, example number 1. Example number 2, I want to talk about a bullet fired from a gun. So number 2, suppose we have a gun here. Not a very good diagram, but you know, as long as it does the job. So this is mass of the gun 40 grams, sorry, 4 kgs, mass of the gun 4 kgs, and mass of the bullet, I'm going to make it, let's say 40 grams, and it moves, it leaves, we call the muzzle velocity or barrel velocity of 500 meters per second. 500 meters per second. So again, here I'm not going to indicate east or something. We're just going to have to the right or to the left. The question says a bullet of mass 40 grams is fired from a gun of mass 4 kgs. A gun of mass 4 kgs. So the question, allow me to remove this just so that we don't confuse people coming, when people who would want to follow what's going on here and they will say, but what was written there? Okay, so a bullet of mass 40 grams is fired from a gun of mass 4 kgs. The muzzle or barrel velocity of the bullet is 500 meters per second. The question is determine the gun's recoil velocity. When a bullet is fired from a gun, the gun moves backwards slightly. The velocity with which the gun moves backwards is what we call the gun's recoil velocity. Well, by Newton's third law, you would understand that when the spring in the gun exerts a forward force on the bullet exerts a force of equal magnitude but opposite direction on the gun. So the gun naturally will have to recoil. As the bullet goes forward, the gun moves backwards a little bit by Newton's third law. So we're supposed to determine the gun's recoil velocity. In other words, at what velocity does the gun shake backwards as the bullet moves, leaves the barrel? So there is your barrel or nozzle, muzzle. So the muzzle or barrel velocity of the gun is 500 meters per second, and we're supposed to work out the gun's recoil velocity. Again, this is considered as a collision, and we're going to use the law of conservation of linear momentum. So how do we answer this question? Well, here's how we answer it. We're going to say our answer. We're going to say total final momentum equals total initial momentum. And we're again taking, according to how the diagram has indicated here, we're choosing to the right as positive. So I'm going to say mass of a gun times V final of a gun plus mass of the bullet times V final of the bullet equals mass of the gun times V initial of a gun plus mass of the bullet times V initial of the bullet. Let's put in what we know. What is the mass of the gun? According to information provided here, is 4. What's the mass of the bullet? 40 grams. Remember, the SI unit of mass is not gram or grams. We have to convert that to kilograms by dividing by 1,000. So it's going to be 40 over 1,000. Don't forget that. And then we have this, because 4 plus this divided by 1,000 is supposed to be 0.04, 0.04. And we have the initial velocity of the bullet. Now, notice something. V final of the gun is what they want us to work out, which is the recoil velocity. But V final of the bullet is the velocity with which the bullet leaves the barrel of the gun. That one is the V final. So, positive 500. V initial of the gun, where the gun and the bullet are stationary at the beginning. You are holding the gun in your hand. So the gun and the bullet are stationary. So we expect the initial velocity to be 0, both of them. These are things that you are never taught in physics. You have to think. That's why physics requires you to think before you can put pen to paper. You have to read the question a couple of 3 times at least, and reason, understand what the question is trying to say, and then some of these things will be actually very clear from the given information. So what do we have here now? We have 4 V final of the gun plus this one here. I can actually cancel out the zeros. 1 2 3 1 2 3 4 times 5, that's 20, is equal to 0. Take 20 to the other side. 4 V final over gun equals minus 20. V final over gun equals, if you divide by 20 both sides, you're going to get divide by 4 both sides, you're going to get minus 5 meters per second. In this case, I'm going to say to the right. Why to the right? Because I chose the right as my positive direction initially here. I chose the right as my positive direction, but the minus sign is telling me it's actually not to the right. So I'm going to say, therefore, V final of the gun is actually equal to positive 5 meters per second to the left. Or you can say, therefore, the gun's recoil velocity is 5 meters, positive 5 meters per second opposite the direction of the bullet. The direction of the bullet. Notice something here. I'm using the word opposite, not different or away from. Opposite, because if the bullet is going east, the gun must go west. This is critical. The word we're using here is opposite. Let me just put it in a rectangular box to emphasize what I'm trying to say. We use the word opposite, not away from or any other direction, but it has to be opposite. Example number 2 completed. Now, I've just spoken about types of collision here. If we are to look back at example number 1 and number 2 to check what kind of collisions they are, then you would see that in both cases the collisions are actually inelastic, because kinetic energy is not conserved. Let's check only the first one. The first example was here. This was the first example. Andrew moving to the east, picking up Ben there, and the two move together. If we want to check what kind of collision happens here as Andrew picks up Ben, we're going to look at total kinetic energy before Andrew picks up Ben and total kinetic energy after. So checking the type of collision in example 1. Checking the type of collision in example 1. Let's look at the diagram here. We have established now that V is 2,4. to the right through our calculation of the law of conservation of linear momentum. Here, this is what we got. This is the final velocity of both of them. So we're going to say, to check the type of collision, we're going to say, what is total kinetic energy initial? This is going to be half mass of Andrew times V initial of Andrew squared plus half mass of Ben times V initial of Ben squared. Let us substitute half. What is the mass of Andrew? Well, it's 60. The question has given us. Here it is, 60. We are considering combined mass of Andrew and the skateboard. What is V initial of Andrew? If you look at the information here, it's 4. And we took to the right as positive, so we're going to have to say squared here. Plus half, what is the mass of Ben? Well, it's 40 kgs. 40 kgs. What is the initial velocity of Ben? Ben is initially stationary. And this simplifies to, let me just grab my calculator here. It simplifies to 0.5 times 60 times 16, and the answer is 480. 0.5 times 60 times 16. It's half times 60 times 4 squared is 16. So it's 480 joules. Remember, energy is measured in joules. 480 joules. There it's 0. Let's look at total kinetic energy final. This is going to be half mass of Andrew times V final of Andrew squared plus mass, half of mass of Ben times V final of Ben squared. And when we do that, we get half. What is mass of Andrew? 60. What is V final of Andrew? Positive 2,4. And we're squaring it plus half. What is mass of Ben? 40. What is final velocity of Ben? They are moving with the same velocity. If we do the maths here, let me just punch this into calculator. We have 0.5 times 60 times, so we can just say, if you factorize this, it will be 0.5 of 100. But anyway, let's just do this exactly how it is written here. 0.5 times 60 times 2.4. We're squaring that plus 0.5 times 40 times 2.4 squared. My calculator here says 288 joules. Now you can clearly see that these numbers are not the same. So we're going to say, since total initial kinetic energy is not equal to total final kinetic energy, comma, the collision is inelastic. Right, let's look at example number 3, where we're talking about a collision which is elastic. This is an example of a collision which is inelastic, because total kinetic energy initial is not equal to total kinetic energy final. Suppose we have one more example here now, maybe 2. Here is example number 3. Now we have 2 trolleys. There's a trolley of mass 4 kgs moving east at 10 meters per second. And there's another trolley here, mass 8 kgs. This one is moving west at 8 meters per second. This is before collision. I'm going to put before collision. And then after collision, we have trolley A Let me call this A, call that B. Trolley A, whose mass is 4 kgs, moves to the left or the west at 14 meters per second. And trolley B, whose mass is 8 kgs, we do not know in which direction it moves. Let's just say V there. The question says, this is after collision. The question says determine V. In other words, the velocity of trolley B after collision. That's A. Number B, what kind of collision is this? What kind of collision is this? Justify your answer with a suitable calculation. Suitable calculation. Now, so, and again, we make an assumption here that the system is isolated. So, we're going to say our answer is as follows. We're going to say total final momentum equals total initial momentum. So we're going to say mass of A times V, and by the way, we have to choose directions. I'm choosing that direction, my positive direction, and I'm having that compass there, north, east. It's easier to say east than to the right. So V final of A plus mass of B, V final of B is equal to mass of A, V initial of A plus mass of B, V initial of B. Substituting what we know, mass of A is 4, mass of B is 8. 4, 8. What is the final velocity of A? 14 meters per second west. So it has to carry minus sign because we're taking that east as positive, west must be negative. What's the final velocity of B? I don't know. There it is here. Car B, this car A. They haven't said anything. Let's just put V there because that's the final velocity of car B. We have to determine that. What is the initial velocity of car A? Well, 10 meters per second east, so it has to carry a plus sign. Why plus? Because that direction agrees with this direction we've chosen as positive. What's the initial velocity of car B, trolley B? It has to be minus 8 because trolley B is moving to the west initially. So this is what we have now. Your calculations, this is 14 times 4, it must be 56 times 4 minus 56 plus 8V is equal to 40 minus 64. Taking 56 the other side, 8V equals 40 plus 56 minus 64. 8V is equal to, that's 96. 96 minus 64, that must be 32. And therefore V equals positive 4 meters per second. In which direction? East. We've determined the velocity of car B after the collision. Question number 2. What kind of collision is this? Justify your answer with a suitable calculation. Remember, I told you the defining condition of elastic collision is that total kinetic energy initial equals total kinetic energy final. Inelastic, total initial kinetic energy is not equal to total final kinetic energy. Remember that. So number B, we're going to test that condition. Number B, testing that condition, what do we have? We are saying basically, number B, let's work out total initial kinetic energy is going to be equal to half mass of A, V initial of A squared plus half mass of trolley B, V initial of trolley B squared. Do not forget to square there. This is half. Trolley A has a mass of 4 kgs. Initial velocity of trolley A is positive 10 squared. Here they are, positive 10 initial before the collision, 4, 10, 8, 8. So the mass plus half, 8 initial minus 8 because it's in the opposite direction. It doesn't matter because we're squaring. So 0.5 times 4 times 100 plus 0.5 times 8 times 64. My calculation, my calculator here says 4, 5, 6, and we know that this is energy. It must be in joules. Let's work out total kinetic energy. EK final. This is sigma notation. That's for total. Like I said earlier on, this is half MA V final of A squared plus half MB V final of B squared. Let's punch in what we know. This is half. What is the mass of A? 4. What is the final velocity of A? Minus 14. We're squaring this plus half. What is the mass of B? Is 8. What's final velocity of B? Well, we calculated here. There it is 4. 4. We square it. On the calculator, we are saying 0.5 times 4 times 96, 196, 14 squared, plus 0.5 times 8 times 16. My calculator, sorry, there is 0.5. I typed 0.4 accidentally. All right, so it's 4, 5, 6 again. Now we can clearly see that these numbers are the same. So we're gonna say, therefore, since total kinetic energy initial is equal to total kinetic energy final, the collision is elastic. Two cases here we've been able to show you when the collision is elastic, and I've been able to show you when the collision is inelastic. Right, I would want to stop here. In my next lesson, I'm going to look at this example here. I'm going to start here. In this example, and this produces the most difficult question on the conservation of linear momentum. I'm going to hide that mass there, and I'm going to hide that velocity there. All the information provided, I'm going to hide this mass, and I'm going to hide that velocity, and I'm going to say that the collision here is elastic. So we're going to work from elastic collisions coming all the way to determining the mass and also the velocity. Right, I hope this lesson has helped you somehow. I recommend that you watch the first one and watch this one. Put the two together. It should be quite meaningful. But otherwise, if you're new to this channel, I'm requesting that you subscribe, share these videos. It's going to help us to grow this channel and give us the momentum to produce many more videos. We'll see you next time.